I am Connor. I use he, him pronouns. I am a data scientist at Nationwide Children's Hospital in Ohio, and I'm going to talk about contextualizing phenotypes in medical notes using language models. So while I'm the one presenting, it's really been a group effort, and Max Emilius has done a lot of the work conceptualizing and implementing the model that I'm going to be talking about today. So the long story short is that we're going to use both small and large language models and natural language processing techniques to perform named entity and attribute recognition on clinical notes to help clinicians and researchers downstream have higher quality phenotypic information and patient profiles. So one of the main use cases of clinical NLP is extracting information from clinical notes. And an important type of information for healthcare providers is knowing the observable traits that are relevant to a patient's medical condition, like symptoms, diagnoses, or other health related observations. And those are known as phenotypes. But why is contextualizing phenotypes important? Let's imagine that we have a clinical note and we're tasked with extracting all of the phenotypes. This is essentially a named entity recognition task. So let's say that we have the text, she was diagnosed with syndactyly of the second and third toes bilaterally and has shown poor weight gain since birth. We've ruled out any hemolytic anemia based on recent lab work. Her maternal grandmother had intellectual disability and her paternal uncle has a history of recent fractures due to brittle bone disease. Parents report no gingival bleeding or bruising, even though we were concerned about possible platelet aggregation disorder. So a contextually naive phenotype concept recognition model will tag all of these phenotypes, but it potentially links them all back to the patient. And that ignores phenotypes that the patient doesn't have, phenotypes that they might have, and phenotypes that are related to the family member. So inappropriately handling the context of these phenotypes can extend a patient's diagnostic odyssey and potentially result in unnecessary test orders that affect patient safety, anxiety, and billing. So I really want to rephrase this and say that phenotype concept recognition is a named entity and attribute recognition task, and shift the focus and put equal weight on both the phenotype recognition and the context attribute. But how do we evaluate contextually aware phenotype extraction? It turns out that it's pretty hard. The current benchmark data sets for phenotype extraction, like the GSC and ID68, don't include gold standard context attribute labels, and popular phenotype extraction models like ClinPhen and PhenoBERT and MedSpacey have limited abilities to assign these context attributes. And I do want to mention that just when I'm talking about context attributes, I'm going to specifically be referring to negation, family history, and hypothetical flags. There's other types of context like severity and granularity, but that's not what we're going to be considering right now. So we set out on a journey to address this gap by first creating a benchmark data set that has context attribute labels, and then training a model that's capable of determining the context attribute of a tagged entity. So to create a benchmark data set with context attributes, we started by manually annotating the current ID68 data set, but we found that there was really hardly any diversity in the context attributes, with over 90% of the phenotypes being related to the patient. And in our real clinical notes, we see much more contextual diversity. So we decided to make a corpus of synthetic documents that are based on the ID68 notes that have more contextual diversity. So to do this, we used Claude Sonnet 3.7, and we first selected an ID68 document for the note to be based on. And then we added the phenotype and context attribute annotations to the document and formatted that with XML tags. And I'll show an example of that in a minute. But then we instruct the LLM to write a synthetic document that's based on the annotated text that's similar in tone and structure. But we want to ensure that the context is different from the seeded document. So we randomly sampled up to 2 OMIM diseases, up to 25 related phenotypes, and up to 3 synonyms for each phenotype, and told the LLM to include only a subset of those terms. We also told Claude to have about 10% negated phenotypes, 20% family-related, and 10% hypothetical. So we generated hundreds of these documents using slight variations in the LLM prompt, and also with different ID68 documents as the seeded document. And I manually reviewed some of them and chose 50 that I didn't have to make any edits or corrections to. And that's what became our new benchmark data set. So this is an example of what the annotated text looks like. That's going to be the input for the generation task. You can see that instead of the normal flat text input, we're going to be adding depth to these phenotypes and telling the model what context attribute to assign with it. And since Claude is trained on text, is familiar with XML tags, this is it's really beneficial for the model, and it understands more about the task that it's doing. And we can see that it successfully increased the diversity of the context attributes in our synthetic data set on the top, and then compared to the ID68, which again is about 90% related to the patient. So now that we have this benchmark data set, our next step is to train a model that can distinguish between these context attributes. And we're calling this model phenocontext. So to train phenocontext, we started with a modern BERT model, and we fine-tuned it using over 13,000 synthetic sentences, and then added in a classification head to perform multi-label classification. So these are our toy examples, but this is what the input would look like. So Connor is nervous, and then that phenotype is surrounded by these special entity tags. And then when all the labels are 0, that means that it refers back to the patient. So Connor does not have a headache is negated. Connor's brother might have a headache is both family and hypothetical. And then when there's multiple phenotypes in the same sentence, that sentence is included as multiple instances, with each phenotype being a separate instance. So Connor has macrocephaly and headaches are both related to the patient. They're all 0s. He does not have seizures is negated, despite a family history of epilepsy is family. So after training the model, we have a macro F1 score of 99.3, and all of the F1 scores are above 99 for negation, family, and hypothetical. So now we're going to integrate the context attribute model back into our phenotyping pipeline and then assess performance. And we assess performance on both the ID68 and our synthetic data sets. And we use 2 popular phenotyping models, ClinPhen and PhenoBERT, as well as the union between these 2 models, which we're calling ClinBERT. And then in addition to the union, ClinBERT includes some conflict resolution logic for when the models tag either different phenotypes within the same span, or when the spans are overlapping but not disjointed. And then in addition, we included 2 contextually aware versions of ClinBERT, one with a custom MedSpacey pipeline and one with our phenocontext model. And we assessed performance with 3 metrics: the span F1, which is just basically the named entity recognition part and matching the character spans; the context accuracy, so for a given phenotype, or for a phenotype that is mentioned, does the context from the model match our gold standard label? And then the term and context accuracy does the phenotype match the character spans, and does the context match? So here is the results for the ID68 data set. So that third line is ClinBERT, and we see that it's better across the board than ClinPhen and PhenoBERT. So that'll be our baseline model. But we also see that adding in the context attributes from either MedSpacey or PhenoContext doesn't help performance at all on this data set. But that's not surprising because, again, 90% of these phenotypes are related to the patient. There's just not any diversity. And then here are the results for our synthetic data set. Again, we'll treat the ClinBERT row, the third row, as the baseline model. We see adding in the context attributes from MedSpacey is not any better, but we do get a significant increase in performance with our PhenoContext model, with about a 32% increase in context accuracy and a 27% increase in term and context accuracy compared to the context naive models. So since this slide is a little busy, I'll just say that again, and that our PhenoContext model gives us a 27% increase in term and context accuracy compared to the context naive model, which again is the baseline or the default behavior for most of these phenotype extraction pipelines. So here are some examples of what PhenoContext did well. It did better when there was multiple context attributes for a given term. So the gradient coloring from red to blue means that it's both negated and family related. It also just did better on hypothetical family and negated instances. Specifically for that last row, the negation keyword ruled out is not in the ClinPhen dictionary to assign negation. And those are pretty easy to modify. You just add it in, but just with the default behavior, it's not included, and our model can pick that up. But there's still plenty of room for improvement. So here are some examples that PhenoContext struggled with. Paternal history negative for lens dislocation or other ocular disorders. That should be both family and negative, but PhenoContext said that it was hypothetical. Her father reports peripheral neuropathy symptoms since his 30s, but has no cognitive impairment. PhenoContext got that it was family related, but it missed negated, even though it's explicit with the no right before it. And then mother denies rod cone dystrophy, but reports decreased activity of gonads in her brother. Rod cone dystrophy was flagged as both family and negative, but hypogonadism doesn't have any context attributes. It just missed that one. So some potential future work is to use real clinical notes instead of the ID68 summaries for the seed documents and the synthetic training instances. And that would allow us to incorporate both narrative and telegraphic statements, as well as incorporate different writing styles from various note types and provider types. And then we also want to assess performance on real-world data sets like Mimic, but we would need to create gold standard annotation sets. And then I'll add this one that's not on the slide, is that we could modify the training instances. Instead of restricting them to one sentences, we could chunk the documents and give the model more context within the text. So an example would be, in a real clinical note, you might have a family history section where, like, the patient's dad has a big head. He also has epilepsy. His brother has 6 fingers. And the pronoun that is in the different sentences refers back to the patient's father, which is mentioned out of context for a single sentence. So if we extend that in the training instance, then we can better generalize to real clinical notes. And that's it. So thanks for your attention. Happy for any questions.
And we are ready to take questions.
There's one from the live audience also.
Okay.
Yeah, I can just yell from here, that's fine.
No, because then people can't hear online.
Yes.
So you're not allowed to yell. Great job.
Thanks.
Are the model or any of the synthetic data online?
They will be soon. We're talking about it. It's not released yet. So I think the benchmark we definitely want to because it addresses a lot of the issues. But I think we need to do another pass of the manual annotation and just ensure and probably increase it from 50. That was just kind of an arbitrary one for the deadline for this. But since we generated hundreds of them, we could easily increase that. And then we can release the model. We haven't done it yet. And then I'm expecting that we'll have different iterations with real clinical notes instead of ID68. So it might be an iterative release.
And the same for the code to generate the synthetic notes?
Yeah. Yep.
Fantastic. While I'm passing the microphone, I'll also mention to the many people on the back row that there are plenty of free seats in there.
Hi, thank you for the talk. I just have a quick question. So in your data, is it possible? Is there a case that the sentence contain two phenotype with different attribute? If that is the case, how to deal with that?
I'm sorry. When the phenotype has multiple.
Yeah, is that the case that context contain two different
Yes.
phenotype but with different attributes?
Yes.
How to deal with that? How to group them together to the phenotypes?
When a single phenotype has different context attributes, that can be included in the training instance. So it's a multi-label classifier, so it'll do each classification at the same time, and so each phenotype can have multiple context flags.
Maybe I missed that part. Thank you.
Okay, thanks.
Thanks for your talk. You showed a few examples where the classification was off, even though, like, from a human perspective, it was quite logical, quite clear what it should have been.
Yep.
Do you have any insights on why they were missed or how that could be improved?
I think, well, it's something that we need to look into further and do like a more comprehensive error analysis. I think it boils down to the training data. And so having more contextually diverse examples and then probably just more examples. So we picked 13,000, but there's no reason why we couldn't do more. And then just giving more examples. One thing I was thinking of is that we had a rule-based pipeline for MedSpacey. So we had these rules that or keywords that we were looking at. We could use those rules to inform the synthetic generation. So we want negation that is informed by these keywords, and then create sentences that include those explicitly. So that's something that we're thinking about.
We also had a question from online. So the question is, why not use the large language model directly?
Yeah, good question. So since we're in a healthcare system, our end goal is to apply this to real-time clinical notes, and there's going to be millions and millions of these. And so using an LLM is just not financially possible right now. So we could work with local models, and I guess we could consider that. But right now, we wanted to also just contribute to the community and have this benchmark data set and start small.
We have one more.
There are free ones open source and then it's more.
Sure, that's what was answered already, that yes, there are free ones online, but they are the local models you're talking about. So
Yeah.
Absolutely. I guess that's also an advantage in terms of privacy.
Yes.
When it's medical records.
Yep.
Using things like ChatGPT is not necessarily an option.
Exactly.
Thank you very much.
All right. Thank you.